Basu is going to give his presentation for about 30 minutes, and then he's going to take questions from the audience, from you folks. Hopefully, find some good questions for him to, answer. And then we'll have a private session with Basu, and that's it. So with that, it's all yours, Basu.
Yep. Okay. So before going into the scope of my research, let me discuss wave energy converter in general. Let me give, few of the people are new to the wave energy converter, so I'll just give a bigger picture about wave energy converter and why it's relevant in today's time. So everybody knows that climate change, everybody knows that climate change is real and it's impacting our life directly or indirectly. The timeline you see on the screen up here is pretty important. It landmarks few of the important years in terms of climate change for us. Starting from 2015, that's when Paris Agreement happened. And that's the year when, for the very first time, human race has come together and agreed on a term like climate change is real, and it's very catastrophic if we don't proper steps right now to resolve it. And in that agreement, around 192 countries signed an agreement to make sure that the global warming temperature don't go above 2 degrees Celsius. Now, to achieve that particular thing, we need to make sure we have our greenhouse gas emission decreased to 45% of what we have in 2010, and we become carbon or like net zero by 2050. And net zero is something, whatever amount of greenhouse gases you generate, you should absorb that much amount of greenhouse gases. And to achieve these targets, renewable energy will contribute a lot. It will be around 67% of our total energy generation in year 2050. So, and whenever we heard about the renewable energies, there would be two names coming in your mind, which is like solar and wind. But there's another key player, I would say, is wave energy converter. Now, this is how a generic wave energy converter look like. Not generic, this one is pretty special, I would say. It's convert basically wave energy into useful form of electric energy using simple like electromagnetic principle. Up here on the figure, you'll see a point absorber wave energy converter. Like it look like that if you see on this in the ocean, but deep inside it have like multiple component. The floating structure is what we call buoy, or some people call it buoy, some people call it buoy. So, and we have a generator inside, which basically you can imagine it would be fixed and the buoy would be moving up and down so that we can generate electricity. And then it will transfer to the base plate, then it will go through the electric cable and we can transfer it to the shore. To give you guys a reference, this is how like industrial, or I would say the real prototype or real working version of a wave energy converter look like. It's a 300 kilowatt wave energy converter from a company called Core Power, and it's like 19-meter tall and 9-meter width. And you can just compare it with 6-foot human. So it's pretty massive structure. And all these kind of wave energy converter, like 100 to 1,000 wave energy converter clubbed together to form a wave energy converter plant, and then they transfer the energy to the shore so that people can use it. Okay, so now let's talk about why they are so relevant in renewable energy mix. This is a pretty cool data you can see on the screen showing the power generation by the waves. And on the y-axis, you can see the power generation, and the x-axis, that's the time. So these big peaks is the power generations by the solar energy. It is pretty high, but if you look at that at night, you really can't, you don't have any energy. So the energy is not consistent, though power peaks are pretty high. In the wind, uh, it's consistent, but it's not predictable. So in that case, like if you look at the wave energy, it is both consistent and predictable, which definitely makes a lot of sense. And it can be a good plug-in to our all renewable mix. So now the question is, if it is that good, then why the heck we are not using it? And for like most of the reason, the answer is economics. The levelized cost of energy is pretty high, which need to be cut down by 50% to make it more economical and so that people can use it. So to cut down the cost, we need to do some research and development. That's the reason we, as engineers, are trying to working on it. And this is the energy equation of the wave energy converter, if you look at it. And it have a main important force, which we call power takeoff force, or PTO force, which is like one of the most important thing. If we can increase, if we can somehow increase the PTO force, our energy generation would be high, and then our production cost will be less, and that's what we want. And for that, we do various experiments, or like we try to apply controls theory on that. The main idea is if we can somehow increase the motion of buoy, uh, more when the waves hit on it, we can generate more FPTO force. We can do that thing by applying the control theory from which we can give the actuation force and make it in resonance with the waves, or we can design different type of buoy shapes, which basically Hussein does, and you can generate more FPTO force. And like to do all this, you need scale down model. And when you make the scale down model on which I worked upon, friction is an important point because when you scale down the model, the friction force won't scale down, and the ratio of friction force would be pretty high. So if you scale down the like the WEC model, which is 19-meter long, then you have to make sure you eliminate all the friction. And that's the reason you need air bearings. That's the reason we use air bearings. There could be much possibilities, but we use air bearings. And I'll be talking about two design, old design and the new design, obviously. So old design is something which was which we had used in the past, and we have like come up with how we can use the air bearing. And the new design is something which we had worked on now, and we have figured out various issues, various challenges we face in the old design. And I've worked mainly on the new design, so I'll be talking about that in a while. So now let's begin with my scope of research. I worked on basically three milestones. The first is designing, the second is characterization, and the third is testing of wave energy converter. I would be calling it WEC from now, but it's wave energy converter. Okay, so the first milestone is designing of low friction testbed, which I would be calling LFT. Okay, uh, so before talking about the design, I want you to look into the component used in testbed WEC. So this is a graphical representation of how how a testbed WEC would be look like. We have waves and the buoy is dealing with it. It's a floating object which basically moves with the waves, and then that motion transfer into the connecting rod, which goes into the voice coil. The voice coil act as a actuator and generator both, but we had used it as an actuator. We didn't really generate electricity from it, but we can use for it for the electricity for sure. Um, and then if you look at the air bearing, this is how an air bearing look like. Uh, it's just throw a constant high pressure air around anything and not anything, basically the precision road which is going inside it, to make sure a constant pressure going across the road so that we have negligible friction. And that's how a voice coil would be looking like. It's a electromagnetic system which have coils and magnet, so that we can use electromagnetic principle on it and use it as an actuator or generator. Now you guys will be thinking around this. This is something different of what you have shown us into the introduction. Indeed, it's very different because this is a wave energy converter which you have seen, which we deploy in the ocean. This is a wave energy converter, which is so-called test bed, which is designed to serve the purpose in a controlled environment. So it would be installed inside like we have MTU wave lab down in the 10th floor, and that's where we install this particular thing. We mount this thing on a wave tank bridge using a mounting plate at the back, and then we do multiple testing on it. In this slide, I will talk about the challenges we had in our old design. So this is how our old design looked like. There's two main challenges with our old design. The first is alignment, and the second is moving assembly was very heavy, and the both are were the serious issue. The main problem was with the alignment. Though we use the air bearing and we don't have any friction, but our voice coil and the casing were not properly aligned. If you look at this picture, casing and the voice coil axis don't match, and the reason was like we have only 0.9 uh, clearance between those, and if we have a marginal error somewhere in the assembly, it will surely have contact between these two. And if we have contact, then everything, the air bearing have frictionless. That doesn't make any sense if we have any friction point in the voice coil. So that thing need to be eliminated. That thing for sure need to be eliminated. The second point is we had a structure which we had designed to avoid any kind of a rotation. So as we can have like any kind of force from on the wave energy converter, and it may rotate. So we developed this particular part where we have anti-rotation links so that it don't rotate. But we really don't need that part because we are again doing the test in a very controlled environment. Only the sine waves we are throwing mainly. So it usually don't rotate, and all these things adds up to like 600 grams, which is a massive weight, and we don't want that weight because like we can test different buoy shapes if we have lightweight. So now let's talk about the new design, which is LFT design. Um, this is how this design look like. On the CAD, it would be looking pretty much the same of what you have seen in the last design, but I'll just try to explain you how it's different and what approach we took. So if you look at, we again have two consideration. We have to, in alignment, we have to simplify it. And the second, for the moving assembly, we have to reduce its mass. So to get the better alignment, we try to approach it in a way where we try to design it in a unibody form instead of using multiple parts. For example, if you look at this particular animation up here, we have 5 parts, and imagine these 2 blocks as a bearing blocks, and we have shaft going in between, and we have voice coil mounted up here. And so what will happen eventually? If you have like this particular part, and if we have some manufacturing error, it will lead into like the part, both the 2 and 3, which is like bearing, and up here we have voice coil, they won't be coaxial, and we want it to be coaxial. And if we make it unibody, then there's good chances that it would be coaxial, and that's what we want. And if you look at this particular design, this is a unibody up here. I will explain you these things in more detail. I'll just try to explain you all these things in 2 type of assemblies of a wave energy converter, which is the moving assembly and the fixed assembly. So this is a moving assembly, which consists of basically all the parts which are moving inside the coil. And the few of the highlights in the moving assembly is using a hollow precision rod. Last year, we were just using a solid precision rod, which was quite heavy. This year, we decided to move toward the hollow precision rod. But to get the hollow precision rod, we need to use something kind of a structure rod connectors, which will be threaded at the end of it, of both at both the end, where we mount the buoy and where we mount the voice coil. By doing this and removing all the anti-rotation part, we were able to save around 58% of the weight, and we were from which 40% of weight reduction is from precision rod. So precision rod give us a really good results. It was kind of a tough to get it manufactured, but yeah, it was a good bet to give. And with all this hard work, we were able to test multiple buoy shapes. And I guess Hussein was happy with that because he worked on the buoys. And these are the different type of buoys which we have used: spherical, cylindrical, hourglass, and con. Now, in this slide, I'll be talking about the fixed assembly parts. Uh, so up here, you can see the laser sensor, which is used to basically measure the position of the voice coil and the moving assembly, uh, even the buoy. And we have plugger, which basically is used to, when we are not using the voice coil, when we are not doing the testing, we just make that plugger inside those plugger slot so that our voice coil can rest on it, and we can leave it like that. The other important consideration was using the dowel pin and the bolts combination in a diagonal manner. So if you look at this particular picture, we have dowel pin diagonally aligned up here, and with the same combination with the bolt. The dowel pin up here makes sure that we mount our bearing at the precision location, and the bolt makes sure it don't move. So using dowel pin and bolt combination just help us to make sure all 3 setups are properly aligned. So this is the combination which we have used everywhere in all the assembly. So after designing it, this is how the manufactured assembly look like. This is the top, front, and side view of the design piece, design wave energy converter, LFT testbed. And to understand it, how cool this thing is, just look at this particular video. So this is the effect of air bearing. This is like slope of hardly 5 degree, and it's like moving pretty smoothly. So that's the reason we were using air bearing to make sure it's become that frictionless. Now, let's talk about the second milestone, which is characterization of the voice coil, uh, for which I use neural networks. Uh, so before I start with the voice coil characterization, I need to explain you the hardware in loop or the instrumentation setup in the wave in this particular design. So we already talked about this, which is like the mechanical hardware part. We have designed this particular thing. This is the electronical hardware part, and this is the software part which we have used. So like we generate our signal-based model in a MATLAB, and then transfer the kind of information which you want to give to the voice coil into the microcontroller, and then it transfer that particular knowledge to the amplifier. It then it give the amount of current which you want to give to the voice coil, and then voice coil moves. And using that particular, like, then we have the load cell data and the position data of the voice coil going back to the space, and then we can see that results. So mainly we target 3 data from all the experiment, which is like the current data, force data, and the position data. All right. So in this slide, you can see the simulating d-space workflow. This is a signal level model to generate various type of input signal. Up here, we have this forward current, block like forward current in which we can give various kind of input. We'll be using constant and white noise and all the experiment which I'll be talking about in future scope of research. Okay. In this slide, I'm showing you how to calculate the actuation force of voice coil using load sensor data. So when we will do the experiment, we'll have the data from the load sensor, but we don't have the load from the voice coil actuation. So for that, we just form the FBD of that particular system, and we got that particular equation from this block diagram. And if you look at the equation one, if we neglect the friction force and assume that our air bearing is working perfectly, then we'll have equation number 2, where Fa is the actuation force, which is generated by the voice coil, and FLC is the load by the load cell, which we measured through the load cell. And if we assume that we move the voice coil very slowly, then equation 3 is what important for us, and we will be using that equation later. Okay, now let's come to the main thing, which is voice coil characterization. Uh, the voice coil we have is from HTW. We have mainly 3 information, which we were. So we mainly have 3 set of information, which is relevant to us, which is the stroke length, which we have, which is 85 mm. The 100% duty cycle of the voice coil is at 2.6 amp, and it gives maximum force of 38.78 Newton. Then for the 10% duty cycle, we have 7.8 amp current, which gives maximum force of 116 Newton. These 2 values are important because it would be pretty useful later in the part. So what actually happened when we move a voice coil, it surely generates some force, and that particular curve look like this. So the curve which you see is not from the voice coil we are using. It's like I find it online, but we need that particular curve for sure, and that's what we call voice coil characterization. And we just don't need that curve for a single current. We need that curve for each and every current value which we can give to the voice coil. And so this is a pretty important thing, and we need that particular thing. I will also explain you why we need that particular curve later in the part, but for now, assume it's very important. And to get that particular thing, we use neural network. So this is a neural network look like. We have input layer and output layer and hidden layer in between. We will give something to the input layer, and that something is input 1 is current, and input 2 is torque position. And the output would be the actuation force, and that's what we want. But to get that particular data, we need to train our neural network model. We need to feed in some data so that it learn about it. Okay, for that particular current value, for that particular displacement value, I need to generate that much amount of force. So for that, we will shortly do some experimentations. So this is like the experimental results when we give positive current to the voice coil. So in total, we did 7 tests, which ranges from plus 2.6 amp to minus 2.6 amp. And so these all results are for the positive current starting from 0 ampere, 2 ampere, 3 ampere, and 2.6 ampere. This is the current data. This is torque position data. This is load cell data, and this is actuation force data. Now, if you look at the load cell data, this is what we get, and actuation force is something which we derive from equation number 3, which I've highlighted you back the 3 slides back. So, and this is a very important plot for us because we're gonna feed in the current data, position data, and this particular data to the neural network. So how we get that particular data, you will see in this particular. So up here, we give a constant current input to the voice coil and it moved completely down. So at that time, the stroke position was 100, and then I'm pressing it, it moved to the 0, and then I'm releasing it, it moved back to the 100. And like I was doing it for 2.6 amps, so the same thing for the 2.6 amp. And then we have, which is, if you imagine it, it would be somehow looking like what I've shown you into the introduction slide of the data which I get it from the online. So this is the data or the voice coil characterization, or I would say force displacement curve of our HTW coil at 2.6 amp. But we need that particular data for multiple amount of currents. But we did that thing for like 7 tests right now. This is for the positive, and these same thing for the negative. And then we form the neural network model on it. So the experiment data is used to train the neural network model, and we use like NF tool for that. Total 10 neurons were used in hidden layer for forming that particular neural network model. And up here you can see the results of the neural network. The regression coefficient R value is 0.995, which is pretty good. So regression R values, if you have 1, it's pretty perfect that whatever data you are giving in, it's getting the right result for that particular data is 1. And if you go, so R value ranges from 0 to 1. So if it's 0.99, it's pretty good. Same thing for the error histogram data. The error generated for the training, validation, and test data was also very less, very close. It's close to 0.2279. So these things, so that shows that our neural network is performing kind of a well, but we need to validate that. And for that, there's like 3 tests which I performed. So for now, just imagine, like, let's try to take an analogy. We have a kid which we have trained, like how you're supposed to ride a cycle, and then we give him 3 tasks, and that are the 3 tasks: case one, case two, case three. In the first task, we are just telling that kid, okay, you know how to ride, so what about now? I'll just keep my hands at back of you, and you will just ride in a straight path. And then in the second case, we're telling the kid, okay, what about now you ride it yourself? And in the third case, we're like, okay, now you're pro, just do the stunt. So that's the approach what we took in all 3 cases. So in the first case, we give a constant current input to the neural network. In the second case, we ask the neural network to extrapolate some of the results. And in the third case, we give some different kind of input, which is sine wave input to the neural network, for which it was not trained before. So if you look at the first case, in this case, we give 2 ampere current input to the neural network, and then compare it with the test data which we have, because we perform the experiment at the 2 amp current input. And the blue line which you see behind is the experiment data, and the red line is generated by the neural network. So and the difference between two is pretty less, floating between minus 0.7 to plus 0.7, which shows that even the curve path is pretty perfect. So that means our neural network is working well, and like our kid is able to ride on a straight path. So we were happy. Now let's move forward. In the second case, what we will do is what we have asked neural network is to generate force displacement curve for the 10% and 100% duty cycle. Now, uh, when we look at our stack sheet from the HTW, we only have 2 points available, which is the like maximum force generation. And these are the max force in the stack sheet, which I've also mentioned you into the introduction slide, that at the 10% duty cycle will have maximum force of 116 Newton, and 100% duty cycle will have 38.7 Newton of force. And then when we plot these curves from the neural network, it almost come up with the very same results. So for the 10% duty cycle, we got the force value of 113, which is like this peak, the blue one. And for the 100% duty cycle, we got the peak at 39.03 Newton, which give us a difference of minus 2.6 and 0.9%. So which is pretty less. And the cool thing is, it's doing that thing for 7.8 amp of current, which is 10% duty cycle. And if you look at our training data range, it's ranged from minus 2.6 to plus 2.6, and 7.8 is something which is far above its training data. So it's like it's predicting something for which we didn't teach him, but it's working pretty well. So it's another good thing to see in a neural network. Now, the third point. This is something which is more cool, because now we were giving some very different kind of input for which it was never been trained. Now we're gonna give sine wave input current to the voice call neural network. And before that, we trained it for the constant current input. And if you look at the results, again, pretty cool. If you look at the force plot from the neural network and the testing results, they almost overlap each other, and the difference value again plot it from minus 0.5 to plus 0.5. So that means, and that particular plot is very special for me. It's because I know I performed that particular experiment by myself, and it's like I performed that sine wave input data somewhere, some other day, some very different day, and my neural network is giving the very same results. It's giving me some kind of a chat GPT vibe, the way I use the chat GPT for the first time. I really got that feeling when I got this results. So yeah, now now let's talk about what are the application of this. You talk a lot about this, like it worked pretty fine. So what? Like how are we going to use it? So we can use this neural network as actuation force lookup table for any physics-based model. For example, we want to do some testing of our wave energy converter. We want to do some 100 tests on a wave energy converter of some control algorithm. So we really can't do on a physical model. We need to make a physics-based model. And up there, we need the information of like how much force you will have for different current input. And up there, we can put that particular neural network, and we can do multiple tests on on that physics-based model. So, and the second, I would say we can inverse that particular neural network. Instead of taking current as an input, we'll take actuation force as an input and displacement as an input, and we'll get the current as output. Now, what will happen with this is, like, we can use that particular neural network to give instructions to our voice coil. For example, we develop an optimization algorithm for, and we know that how much optimum actuation force we should give to generate the maximum PTO force. For that, we can give that instruction to the neural network that we want that much actuation force, and at that particular displacement, it will give us the current value, and we can use that current value and we can put that current value in our voice coil, and it will move uh, according to that particular, and it will generate that force value. So that's another cool application for this particular model. Okay, now let's talk about the third milestone, which is testing. In this, we will talk about how the design LFT WEC is validated for its natural frequency using test and theoretical results. So the idea is we will test the spherical buoy submerged in a water at 2 draft and calculate its natural frequency. The 2 draft are mid draft and the high draft. And then we will evaluate its natural frequency by experimentally and then validate it theoretically. So you will observe that when our buoy is at mid draft, that means the water and the buoy have interaction at this particular point where when your DM is 10 centimeter, you will see high frequency, and when you go to the high draft, you will see the low frequency. Now, this is the test result. White noise current input is given to the amplifier. It's a band limit frequency of 10 hertz is given is inside the white noise, and we can see the position and the force outcome from from our model. And if you look at, this is how it's look like while testing it. Oops. Mhm. So when you give the white noise input, it throws like multiple type of frequencies to the voice coil, which move it up and down. For few of the people, it may look like what exactly this noise is, but this noise is pretty useful because you can give a good band of various frequency to the to a system and see how it's performed under various different frequency. And you will see how these data which you see is useful in the next. So we got that particular data. Now that's the use of that particular data. We use that particular white noise data to generate the transfer function of our wave energy converter system at 2 different draft length. So this is our transfer function at midline draft, where we have current as an input and position as output. And up here, you will see that our peak is at 10.3 radian per second, which is our natural frequency when our buoy is at mid draft. We did the same thing for the high draft. And up here, you will see that our natural frequency moved down to 9.24 radian per second. All right. So we use now we calculated the natural frequency theoretically. Up here you see the just a second. Up here you see the second order ODE form. Probably everybody know about this particular equation. We can form a very same equation for a WEC hydrodynamic model. Tanya and Hussein work on this, so they help me out with this thing to figure out what's the natural frequency theoretically. This is the nonlinear buoyancy force, and this is the radiation force, and these two values will result into the stiffness and the mass matrix of the wave energy converter. This is a generic equation which can generate the natural frequency of a spherical buoy uh, at various different draft length. D is the draft length which will be changing, and if you look at this, these are the theoretically calculated natural frequency 9.9 and 9 for the mid and high draft respectively. And then you got then if you compare it with the measured result, you get the 4% and 2.5% of the error, which is less, but it's there. So now the question is how how is natural frequency important in WEC? And to like the answer is to maximize power generation, the natural frequency of the WEC buoy system should match the natural frequency of waves. And the reason is Hussein helped me out in figuring out this thing, and it's pretty cool thing to think about. So if you look at the natural frequency, so imagine it's a night time and the frequency of ocean is pretty high. At that time, we may prefer the mid draft of a buoy because we know that at mid draft, the natural frequency of a buoy is high. And at daytime, the natural frequency of the frequency of waves is less. So we'll prefer the high draft because we know that the high draft of the buoy has less natural frequency. And the important point is we want that. We want our system to go towards the resonance, because if we move toward the resonance, then the buoy will move more up and down, which will generate more FPTO and more energy. And that's what we want to decrease down the cost of our wave energy converter. So I want to conclude my slides In terms of design, we established a robust and efficient. In terms of design, we established a robust and efficient frictionless WEC test bed setup called LFT. The total mass of the moving assembly is 712 grams. The voice coil trained neural network demonstrate the remarkable ability to extrapolate the results beyond its training data. It accurately predict the force displacement curve for 7.8 amp input with only a 2.5% deviation in a peak value compared to the specification sheet of the voice coil. And the third is white noise testing results in close and align with theoretical natural frequency results. Calculate the WEC model with a difference of only 4 to 2% value. This underscore the effectiveness of our WEC design. Oh, okay. In the end, I want to. Okay. In the end, I want to thank my professor, Dr. Gordon Parker, for guiding me in this journey. And I really want to acknowledge him. He came in mid of his sabbatical to help me out in few of the experiment. Uh, I'm sorry for that, but also but also lucky that the things worked out because of him. And I also want to thank Marty, who helped me out and get that thing fabricated. It was like really great input from him. He was always pretty supportive. I don't know if he's hearing me right now or not, but I really appreciate that guy. Hussein was also great help for me. He's also my neighbor, so whenever I have doubts, I just go up and talk to him. And if you talk about Tanya, she was instructor in 4775, so I learned a lot from her. If I have some doubt, I always go to her, and she's always there to help. I also want to thank my friends and family. I want to thank my family for calling every day and asking me how was your day, which is always it was okay. So that's it. That's from my side. Now, if you have questions, please let me know.